Hello, my name is Seth Gouldred, and I will be giving a brief presentation over fission, how it works, and the commercial application in the United States. I chose to present on fission because I have little understanding as to how nuclear power works. Since fission is the fundamental groundwork that makes nuclear power possible, I chose to research and present on that topic to further my understanding. Here's an outline of the topics to be discussed. First, I will describe the fundamentals of fission and how it works. Next, I will describe how power plants in general operate to produce electricity. I will then relate how nuclear fission can be applied to a general power plant, leaving us with a nuclear power plant. Finally, I will discuss briefly the commercial use of nuclear power in the Tennessee Valley and the future scope of nuclear energy as well. Nuclear fission is founded on the principle that an atom's nucleus can be split apart. When the atom of a nuclear fuel absorbs a neutron, the atom will fission into two smaller atoms and release 1 to 3 neutrons. The neutrons are used to fission the next lot of nuclear atoms, and the process continues. When this is done, a tremendous amount of energy is released. This energy, when let out slowly, can be harnessed to generate electricity. Nuclear materials most commonly refers to fissile materials that are capable of sustaining a chain reaction in a process that releases energy called nuclear fission. The materials include isotopes of uranium, thorium, and plutonium. Various forms of uranium and plutonium are the most common materials used for nuclear power and nuclear weapons. The generation of electricity is a great benefit, but a hazard associated with nuclear power generation is that if the energy generated due to fission is let out all at once, it makes a tremendous explosion in the form of an atomic bomb. The diagram shows an example of a power plant which is modeled using a Rankine cycle, which uses water as the working fluid. The basic steps of the process are as follows. Water enters the pump as a saturated liquid and is compressed to the operating pressure of the boiler. The water enters the boiler as a compressed liquid and leaves as a superheated vapor. The boiler is basically a large heat exchanger where the heat generation originates from combustion gases, nuclear reactors, or other sources. The superheated vapor enters the turbine where it expands and produces work by rotating the shaft connected to an electric generator. There are many variations of power plants based on a Rankine cycle, which include the application of high and low pressure turbines, as well as reheat functions to help improve cycle efficiency. Once the steam passes through the turbine, the pressure and temperature of the steam drop, passing through the condenser. The condenser is a large heat exchanger which rejects heat to a cooling medium, such as lake, river, or even the atmosphere. The steam leaves the condenser as a saturated liquid and re-enters the pump, completing the cycle. Now we will discuss the nuclear application using fission as heat generation for the cycle to the power plant model previously shown. The application of nuclear fission takes place in the containment structure and serves as the operation that generates steam, whereas other plants may use an alternative method such as burning coal. The energy released from the fission of uranium pellets heats up the pressurized water in the primary water circuit. The water in the primary circuit passes to the steam generator and operates in a heat exchanger, typically a shell and tube, which vaporizes the water in the secondary water circuit. It is this steam that passes through the turbine to produce electricity. The water in the secondary circuit then passes through the condenser where it interacts with another heat exchanger containing water from yet another tertiary water circuit. The tertiary water circuit serves the purpose to drop the temperature of the water in the secondary water circuit, allowing it to be pumped back into the steam generator, thus repeating the cycle. All water circuits are independent of each other, meaning there is no direct mixing of the fluids. The commercial application of nuclear power is evident across the world and even in our local community. TVA's nuclear power plants contribute about 6,600 megawatts of electricity to the power grid, making the nuclear power group an integral part of the 7-state power system. About 30% of TVA's power supply comes from its 3 nuclear plants: Browns Ferry near Athens, Alabama, Sequoia in Soddy Daisy, Tennessee, and Watts-Bar near Spring City, Tennessee. These plants alone make enough electricity to power more than 3 million homes in the Tennessee Valley. Now for the future scope of nuclear power. The future looks bright for nuclear energy, especially when considering the advantages when compared to other forms of energy generation. Nuclear energy by far has the lowest impact on the environment since it does not release any gases like carbon dioxide or methane, which are largely responsible for the greenhouse effect. Another characteristic of nuclear energy that promises a bright future is the reliability of the system. Unlike traditional sources of energy like solar and wind, which require sun or wind to produce energy, nuclear energy can be produced even in cases of rough weather conditions. The cost of uranium to be used as fuel in generation of electricity is actually quite low, and coupled with the fact that only 28 grams of uranium releases as much energy as produced from 100 metric tons of coal, holds a promising future for the nuclear power industry as a whole. This concludes the extent of my presentation. Shown are the references used in the construction of this presentation as well as my contact information if you have any questions. Thank you for your time.